Electrostatics 16, the Gauss Law still continues. We'll pick up where we left yesterday. To derive Gauss Law or to prove Gauss Law, from Coulomb's law. After I finished it, you just tell me, you should raise questions. Say we have a point charge like this. Around it, there will be a field which has got some radial symmetry like this. What is radial symmetry here? At the same distance from the charge on all the sides, E is same. The same distance, of course. Like if I consider R from the charge in any direction, the field at that point would be same. Or if I take one sphere of radius R, on the sphere, E will be kq by r square from Coulomb's law. Right. Now, how do I prove Gauss's law from here? Let me see. First, let us recollect what Gauss law is. What is it? Integral E dot dA over a closed surface is equal to charge enclosed by epsilon 0. This is the statement of Gauss's law. Okay. Now, that I want to get. So let me imagine one. Let me imagine a spherical Gaussian surface of radius r. This is a spherical Gaussian surface of radius r. Now, as usual, the method requires that I need to consider one small elementary area here, dA, whose direction is in this way, isn't it? Our job is to find out flux and show that that's equal to Q enclosed by epsilon 0. So flux phi E equals integral E dot dA. Okay, so this will be the way we wrote it is EdA cos 0. Angle between E vector and dA vector is 0. Okay, cos 0 is 1. So EdA. By guessing E to be constant all over, I can take E out of the integral sign and I'll write dA. This will be E into A. But E is known to us from Coulomb's law. for a charge q at a distance r, 1 by 4 pi epsilon 0 q by r square is the field strength. Isn't it so? So I'll put it here. 1 by 4 pi epsilon 0 q by r square into a for the sphere is 4 pi r square. So I'm ending up with what? Q by epsilon 0. Tell me now. So this is proof of Gauss's law from Coulomb's law, right?
Yes.
Yesterday, I was finding out E using Gauss law. Do you remember?
Yes, sir.
In other words, I was proving Coulomb's law from Gauss law, because by using Coulomb, this one, Gauss law, I was showing that E is 1 by 4 pi epsilon q by r square, which means supposing we did not know Coulomb's law, we could have discovered it from Gauss law. Tell me. So your question is welcome now. Come on. Finish it off. But depending on what you're going to ask, I'll continue my discussion. Aryan. But this particular heading is very important, Gauss law. Any questions, please? Now, shall I continue?
Yes.
Yeah, let me see. Now, since you did not ask a particular question there, I'll be still doing what I intended to do, but I will not tell you why am I doing that. After doing, we will know it. Solid angle, let us define. Until now, what we know is a plane angle, right? This is plane angle. It will tell you change in the direction like that. Like this was one direction.
Yes.
So from there, if you rotate like that, it will tell you how did the direction of this got changed. So plane angle is that. Basically used for rotation. Okay. See, if I have something like this, whatever it is, if I keep moving it like this, it is translation. But if I fix it like this and turn it, it is rotation, isn't it?
Yes, sir.
In translation, this direction is not going to change. But I fix it here and turn it, it tells you the directional change, right?
Yes. Yes.
So angle has certain purpose like that. Now, what is solid angle? Generally, we say it is angle in 3 dimensions, but remember, it is simply fix it here only, this thing. Now, just revolve it around it like that, forming a cone. Do you follow? Like this. So this whole thing is called solid angle. Actually, plane angle is between 2 lines, but whereas solid angle will be an angle subtended by a surface. What do you mean by that? Let us think of this surface only. From every point of this surface, choose some point, either here or here or here, doesn't matter, because depending on the point, there you'll find the solid angle. So here, if I consider a point, just keep joining every point in this surface to what? The point. So this, whatever you get, is what you call the solid angle. Okay. And if plane angle is measured in radians, solid angle is measured in steradians. Why am I talking about solid angle? You will know slowly. I told you already. You wouldn't ask the doubt when I derived that thing. The doubt could have been like this. I'll tell you. We said that we are deriving or we are proving Gauss's law by applying Coulomb's law, right? For that, I took plus Q. And around that, we have the field pattern like this. And we showed that flux enclosed is Q by epsilon 0 by taking E as 1 by 4 pi epsilon 0 Q by R square. That means we took the help of Coulomb's law, right?
Yes.
Now, for that sake, I've taken one spherical Gaussian surface like this. Okay. So a question should be like this, generally speaking. Okay, you took a spherical surface and you could write E. But what if I take some zigzag surface? How do I write E and prove Coulomb's law for a point charge, for example? Gauss law from the Coulomb's law for a point charge. Because when we mention Tejas, you're not coming every day. Are you? Look, if I take some zigzag surface like that, E dot dA equals, when you calculate, and we showed this to be equal to Q by epsilon 0 by writing E equals 1 by 4 pi epsilon 0 Q by R square. Now, if I take some zigzag surface like that, I don't know what is E, right? Hello?
Yes.
I don't know what is E. So I won't be able to prove Gauss law if I took some other zigzag surface. Do you follow my point?
Yes.
Because it should be same whether the surface is the spherical surface or this surface, because both are enclosing the same charge, right? Unless I show that for any other surface around Q, flux is same, it's not complete that the process of proving Gauss law is not complete. Tell me. Supposing if flux was different for this and different for this, I mean, if the flux was different for this surface and this surface, Gauss law would be wrong. Why? On the right hand side, we are saying that it is equal to Qm enclosed by epsilon 0. If flux is different for a spherical surface and a different surface like that, of a surface of a different shape like that, how can I make this flux is equal to same Q by epsilon 0? Do you get my point?
Sir, meaning the shape will be different, but if areas are same.
Yeah, that means you are catching something, but it's not area business. But tell me whether you understood the question, because I directly started solid angle.
So like for a spherical surface, we know it will be from Coulomb's law, we know, but for an irregular surface, we don't know, so we cannot apply Coulomb.
This statement, actually, you weren't able to complete. You did not follow whatever I was telling you. When we said flux enclosed by a closed surface is equal to charge enclosed by epsilon 0, we mean to say that the surface could be anything, isn't it? Not just a sphere.
Yes.
Only then the law would be right. Do you understand my point?
Yes, sir.
If I say it is true for a spherical surface and not true for some other surface, the whole statement is meaningless. That is, flux enclosed by, or flux through a closed surface is equal to flux through a closed surface is equal to charge enclosed by epsilon 0 will not be right if it is not right for any surface, isn't it? Yes. Tell me.
Yes, sir. We're defining.
I can just leave this and still manage, but even some problems will be really done properly, meaningfully, simply if you know what is solid angle and the proof of Gauss law in a general sense. So what is that statement I am making? Can you repeat? Though previously we said we proved Gauss law here by using Coulomb's law, we have not yet proved it properly, I'm saying, because we took one spherical surface, which was easier for me to write for E. If I take some other irregular surface and then also if I show that flux is Q by epsilon 0, hello?
Yes.
Then it is actually proving Gauss law.
So we need to prove it in general.
Yes.
Not a
Very, very important idea I'm talking here. I want people to speak. Vaishnavi M. At least
yes.
the statements I mentioned. I'm going slow, right? I'm talking very slowly. Only I'm asking you to think. Vaishnavi.
So
We said flux through a closed surface. You understand? Through I am saving every time. What do you mean by that? When I said flux through, in my mind, I have this kind of an idea. There are field lines. They should be piercing through that. Either they come into the surface or go out of the surface. That is a material. Through, like water flowing through a frame which I put in front of a stream. If that water was flowing parallel to the frame, rectangular frame I put, there'll be no water flowing through the frame. Do you follow my point? I
yes.
took some rectangular frame like this, and I'm putting in front of a stream in whatever angle, doesn't matter. Sometimes I might have put it like this, sometimes I have bent it like this, but finally water flows through that. If I place this frame this way, parallel to the streamlines here, parallel to the flow of water here, there is no flux through that. That is the meaning of flux. Intuitive meaning of flux is that. Whether people followed it, I don't know. So that's the reason I am saying every time that electric flux through a closed surface. Electric flux through a closed surface means the word through is meant for what? The lines of field making holes and going through the surface. Whether they go perpendicularly, slantingly, doesn't matter. As long as these field lines appearing to make holes and go through that surface, only flux is there, remember. Okay, so flux through a closed surface is equal to charge enclosed by the closed surface is the Gauss law statement. So when it is told like that, if it is not true for all kinds of surfaces, it wouldn't be a law. That's what I'm telling you. Do you follow that? Now
Yes.
we'll show that as long as the solid angle made by the surfaces are same, the flux is same. And that same flux is equal to what? Q by epsilon 0. So that is justifying Gauss's law. What did I say? You might take whatever shapes of surfaces around this charge, doesn't really matter. But if all of them make the same solid angle, then flux is same for all the surfaces. And that same flux is equal to that same number called Q enclosed by epsilon 0. So that's what we are going to prove now. In that connection, we require to talk about this solid angle business. Tell me, Aryan. Now, to understand what is solid angle, just imagine ice cream cones. So this is what we mean by the solid angle. Solid angle made by this surface or this surface. Both mean same. You join them, I told you already. From the edge of it, you keep taking lines and join to the point there. And the other side also. Do you follow? If they're joining here, what is there in between them, this 3D thing is what you call the solid angle. If the point was somewhere here, it would be different. The same surface like this will make different solid angles at different points like that. Okay. Do you
Yes.
follow? This phone. So what is the solid angle made by this phone at some point means just you'll take lines like this and join at that point. That space in the middle is characterized by the solid angle. It will be nothing but, remember, like the cross section will be like a cone. Revolve this side around like this. What you trace out is a solid angle. This is the plane angle. This is the plane angle, theta, the semi-vertex angle of the cone. You follow my point? If I joined only this and this, I mean, you may join everything, you make a cone, but in the middle you cut like this, that forms a semi-vertex angle of the cone, right? This is not the solid angle. Just turn around like this. So that space you described, that space you enveloped, is what you call is quantified by the word called solid angle. Do you follow that? And remember, whatever surface you take, whatever shape of the surface you take, at this point Q, at this point where Q is placed here, this one, the solid angle would be same. And that put together, the inverse square law nature of the Coulomb's law makes Gauss's law correct, which I'm going to show you now. Do you follow?
Sir?
The inverse square nature of the Coulomb's law, that is E is inversely proportional to R square, plus the idea of solid angle will show that whatever the shape of the surface you take there, the flux is same, and that same flux is equal to Q by epsilon 0. I defined in the beginning itself what is flux. I did not simply directly connect it up with charge. I defined flux first, isn't it? So try to differentiate between the definition of flux to Gauss's law, then you'll understand my words.
Sir? So if the solid angle is same for different shapes, the flux will be same?
Yeah, but that is happening because one more extra thing is there. The E being inversely proportional to R square.
Yes, sir. And solid angle we're using to prove Gauss's law for any shape.
Yeah. Now, I defined elementary solid angle d sigma. Sigma or omega, that is. I said sigma. It's not sigma. It is d omega, capital omega. Okay. Hello.
Yes, sir.
You know, d omega. Omega like this. Greek.
Yes, sir.
D omega equals d a normal by r square. What does it mean? I'll show you. What Vedanti Rao? Why are you going out and coming in? Now, what is the meaning of that? I'll show you. Actually, don't say that, sir, I did not know solid angle. There's nothing like, if you already knew, there's nothing like to be told again, right? So you need to keep learning new things. Look at this. at a point here, I'm talking of that point I'm taking here. I want to know the solid angle subtended at that point by one surface like this. The surface is not straight, it is bending somewhat. Do you understand? I'll just draw it again. I want to tell you what is dA normal. Huh? I wrote dA cos theta by r square, right? So what is it? I'll show you. Let me take it a little more bending. So what is the solid angle by this surface? I would like to know. Okay. So this will be a D. I mean, I just made it look big, but it is a small thing we are taking. dA, this is. You know what is dA normal? The shadow of this. The angle between this and this is theta. This yellow one is a projection of this area. If this dA, this is dA cos theta, and this r is same for both. It's a very small thing basically. So solid angle here is solid angle made by the actual surface, the white one, children. Do you follow? Actual surface is a white surface. So this white surface makes an angle, solid angle so much here, which is equal to this normal component of that. You understand that? Hello?
Yes, sir.
If this is dA cos theta, it will be like this. This will be theta, this is dA cos theta component. So this dA cos theta as a vector I showed it. Do you follow? But components are not vectors anyway, but for understanding sake, I'm just showing it like this. If you take another area here, for example, that may be dA cos equal to the component of this way. Okay. I don't know if I called it dA1, the dA1 equals dA cos theta. That's what I mean. Okay. So in other words, instead of taking another angle here, another surface here, I'm saying that this is the shadow of this actual surface. Huh? Hello, which will be normal to this means, like if you imagine one sphere like this. So this will be R, this will be R. So this is the normal area we made to see. It's a very small one, try to understand. I just showed it big like that. So this dA cos theta by r square is the solid angle. Can I continue? Hello, children.
Sir, dA cos theta be the
Area which is making 90 degrees with R everywhere. That's why I completed the circle here.
Yes.
Actually, it's a very small one, but very small I cannot show, so I just made it look big.
Yes, sir. Got it.
Everywhere, like you draw a tangent here, this angle will be 90. Can I continue?
Yes.
I'm continuing. Let us see. People are anyway, whatever I said, the people who don't even speak. Very funny kind of a group we have. Now look at this. To understand it, I'll tell you, say I have a sphere. to understand solid angle, I'll just put a sphere. At the center, what is the solid angle made by the sphere? We would like to know. Okay. At the center, what is the solid angle made by the sphere? It will be 4 pi. How do you know? Do you know how?
Sir, we take the area.
It is 4 pi r square by r square. Tell me, everywhere this is r. A small thing you take like this. This is the solid angle. This area by r. Do you follow? This is the normal area itself. Try to understand. If I had some other thing, even that would make the same solid angle because its projection is only this. Okay?
Yes, sir.
But if it is looking somewhat not so clear, I'll just go for a general derivation for the solid angle. This is an important thing. At least the result you are supposed to remember, if not the derivation. But for people looking a little higher goals, both learning goals and exam goals should really understand it. Now, instead of taking the full sphere, I'll take only a part of it. At the center of this, what is the solid angle? We would like to know. Do you follow?
Yes, sir.
So I'll just simply rub this off. Let me describe these sides by theta naught. This is theta naught. This is theta naught. What is theta naught? It's not the solid angle. It is the
plane angle.
Semi-vertex angle of the cone formed when you cut it in the middle like that. Okay, this is our cap. You follow? I can even put this whole thing. This is the cap. To get the 3D picture, I put it like that because that was looking only like a line. Hello.
Yes, sir.
I told you already, every time you need to know what is the angle made by the surface edges at a point. Hello?
Yes.
Now, how to find out the solid angle made by this? And do you know what is this cone? I told you already. Just take the cross section. Somewhere you cut like that. The plane which looks in the middle of these things is a conical. What do you call? I mean, it looks like a plane angle, isn't it? But this is also called semi-vertex angle of the cone, right?
Yes,
The cone you'll get here, isn't it?
Yes.
Yes.
I don't know whether people understand. All this is the surface. The cap you put is what I put here. Hello. So
Yes.
what is the solid angle made by that cap somewhere near the chin or somewhat below the chin? You would like to find out. and this theta naught are the semi-vertex angle of the cone. Okay, what should I do for this? We are going to show that this is omega equals 2 pi into 1 minus cos theta naught. Derivation we have to do actually, but if it is like this, we are going to prove this by taking some elemental area and then finding out the solid angle. So if this is the formula, for example, omega equals 2 pi into 1 minus cos, what is the total angle made by the sphere at the center?
2 beta.
Sphere means like this angle.
Uh, 180 degrees.
Yes. Should I write cos pi? Isn't it?
Yes, sir. Minus.
So what do I write now? 2 pi into 1 minus 1. This is what pi? Hello. Take half sphere, you'll understand it even better.
Yes.
So what is this angle? Hey, come on, I showed you. If it becomes like this, half sphere, it becomes, what is this angle?
Pi by 2, sir.
Pi by 2, right? So for a half sphere, solid angle at the center is 2 pi into 1 minus cos pi by 2. So but if it is neither half sphere, not full sphere, some cap of the sphere there, it is 2 pi into 1 minus cos theta naught. Tell me. You know, this angle. So from here to here, this angle is pi. This is pi, right? But if it is only here, it is pi by 2. Hello. I have not yet proved it.
Yes.
Proving requires some kind of an integration. Actually, you should know that math students, they should know why integration is used only, isn't it? Integration could be used to find out areas, volumes.
Sir.
Hmm.
So whatever shape we take, a normal component will always be a part of a circle.
Normal part will be always a part of the circular sphere.
Sphere, yes.
Sphere.
Yes, sir. So that's why we are taking it.
Yeah, that's correct. Okay.
Yes, sir. So the radius of the sphere and the
that area divided by radius of the sphere square, we need to write. That's correct.
Yes.
Ultimately, that is the bottom line.
Done.
Others, please. This proof I have not yet shown it. Okay, but first understand it, apply it. If you want, I'll show the proof also.
Yes, sir, we'll do the.
Now, I'll go for proving Gauss law in a systematic way, or justifying Gauss law. Instead of word proof, let me say justifying Gauss law. Why am I saying justifying? When we said, I'll repeat my statements again. When we said flux through a closed surface is equal to charge enclosed by the surface, that word surface is not a unique surface. It can be any surface, right? Only then it becomes a law. Do you follow my point?
Yes.
Otherwise, if it is different for different surfaces, where is the law? Huh? Hello?
Yes, sir. It should be in general.
It should be in general. Yeah, generalization is making laws. Try to understand. So that much, if you understand, my job is done. Okay.
Yes,
Now
sir.
look at this. Let me take a plus Q charge here, point charge, from where the field lines are going like that. Okay. Now, let me consider two areas. One, of course, one at this point, at a distance R1 from the point charge, another there at R2, but this is this way. I'll use yellow. This surface is, this surface is like this. But this surface is like this. Do you follow? Do you understand what I did? This is my A1. This is my A2. Hello?
Yes, sir. They're inclined to different.
And I want to show that this is my projection of this. Hello? This is the projection. Part of a sphere, this is.
Yes, sir.
Now, let me say this angle is theta. Okay. Hello. Now, let me calculate phi1 through this. And let me, phi1 equals how much, phi2 equals how much I would like to calculate. Hello. Could you understand the surface which I took? The actual surface is this, children. This is only the shadow of it. This is only the shadow of the surface. Actual surface is this, which is A2 like that.
Yes, sir.
I would like to find out the flux through this and this. All right.
Yes, sir.
Now, flux through 1 is E dot dA, isn't it? Which is EA1, isn't it? E1, A1. Here, field strength is E1, field strength is E2, let us suppose. So, is it E1, A1 here? Hello, this A1 is all the time along the field lines. Hello.
Yes.
Hello, do you follow that? That's why we're calling it a normal area. I don't know whether you understand. This is along the outward normal, right?
Yes,
Even A1 cos 0. This one is what? E2, A2.
Cos theta.
Isn't it? This is my E. So E dot E2 dot A2 is E2 A2 cos theta, isn't it?
Yes, sir, because projection.
Actually, this is a very small one, but I made it look big. Okay. Now, what is phi 1 by phi 2? E1 A1 by
E2 A2 cos
A2 cos theta. Look, solid angle omega 1 equals, what is it? A1 by R1 square. Solid angle sigma 2 equals, omega 2 equals what? A2 cos theta by R square, R2 square. That's how we define. Just go back and see. Huh? Hello.
Yes.
And E1 equals, E1 is inversely proportional to R1 square. E2 is inversely proportional to R2 square, whereby E1 by E2 will be what? R2 square by R1 square. And sigma 1 by sigma 2 will be what?
A1
A1 by A2 cos theta will be what? I'll write here 5 1 by 5 2 is E1 by E2 is what? R2 square by R1 square.
So we get it equal to omega 1 by omega.
Yeah, this is sigma 1 is this, sigma 2 is this, means aren't they making the same solid angle here? Do you follow my point?
Yes.
We see that. We see omega 1 equals omega 2. So what do I write? A1 by R1 square equals A2
Cos theta by R2.
R2 square. So A1 by A2 cos theta is what?
E1 by E2.
A1 by A2 cos theta is R1 square by R2 square.
Yes.
So E1 by E2 is R2 square by R1 square. A1 by A2 cos theta is R1 square by R2 square. So what is this one? So 5 1 equals 5. First of all, do you realize that these two things are making the same solid angle or not? First of all, isn't it? You join these things, no? The same solid angle they make here. Though this surface is this way, this surface is this way, they are making the same solid angle. So that's why I wrote what? A1 by A2 cos theta is R1 square by R2 square. E1 by E2 is R2 square by R1 square because of what? Coulomb's law or inverse square law. So therefore, I showed that 5 1 equals 5. What does it mean now? In inverted commas, I'll put. Supposing, okay, before that, let me tell you. Say this was not inverse square law. It was somehow E1 was inversely proportional to R1 cube, for example. What do I get there? 5 1 by 5 2 equals R2 cubed by R1 cube into R1 square by R2 square. What will I get? R2 by R1. So flux would depend upon radius. That means flux is not going to be same. So inverse square law is the reason for existence of Gauss law, but we'll add something here. As long as the solid angle is same, as long as solid angle is same, flux is same. What do you mean by that? For all, for any surface. So since these two surfaces are making the same solid angle, the flux going through the same. You can see, same lines are piercing through the surface, isn't it? I don't know whether you understood it.
Yes.
This is going normally. Normally means like along A. See, A vector and surface are normal to each other. I don't know whether you understood. If I'm saying that they're going along A, they're going normal to the area. Okay. But here they're going normal to the projection. That's why flux through this real one is equal to the flux through this projection only. I told you already in the beginning itself. So, but since they are making same solid angle, same flux is going through them. And since E1 by E2 is R2 square by R1 square, flux became same. So now we can say with confidence that Gauss law is right because it doesn't depend upon the shape of the surface. Say, for example, previously I took one spherical surface. Take some zigzag surface and keep taking the solid angles of each small parts. Finally, they'll make a solid angle same as this. This one. I don't know whether you understood. You could take any kind of a surface there. Now its projection will be, the projections of all those smaller parts will be becoming only a sphere, and that will make the same solid angle as the smaller sphere. Do you follow?
Yes.
So that's why Gauss Law is correct.
So here A1 is parallel to A2 cos theta.
A1 is parallel to A2 cos theta, correct.
So can we say if the surfaces are parallel, then the solid angle will be equal? Like if the surfaces are parallel, will the solid angle be equal?
This surface and this surface are not parallel, no?
I mean, projections are like A1 and A2 cos theta.
That's what we are saying. This surface need not be that surface, Riya. I don't know what you're saying. This surface could be some other surface like this, doesn't matter.
So like its projection will be A2
Same.
cos.
Yeah. Okay.
Yes.
That's what it is about. Complete it. But whatever you followed, I have no problem, because when I use it in the problems, be careful. Huh? A simple question I'll tell you to understand. Why did I do all this? Say, for example, I have got one cube, cubical Gaussian surface, or a real cube, doesn't matter. I put one charge at the midpoint of the cube. Huh? What is the flux to the cube? Hello? Flux to the cube is q by epsilon 0, right? Because the whole cube is enclosing this cube.
One charge, yes.
Right. And what is the flux through each face? Q by 6 epsilon 0, because each face makes same solid angle. So flux lines will be equal in number. But supposing for the same cube, for example, I don't put my charge at the middle, I put the charge somewhere sideways here, total flux would be still same, because total number of lines will be going through the cubical surfaces, the sides there. But the moment I move it somewhat off center, this is center, for example, this will make one solid angle, this will make another solid angle. So it won't be divided equally for all the surfaces. I don't know whether you understood the whole thing.
Yes, sir, because charge enclosed is the same.
Come on, the field lines will be going through a solid angle. Try to understand every time. That is inverse square nature of the field. So if I placed plus q at the middle of a cube, the total flux is q by epsilon 0, because the whole cube sides are enclosing the cube, and flux through each face is also same. Q by 6 epsilon 0, so q by 6 epsilon 0, q by 6, q by 6, like for all the sides, it is equally divided. That means if I had 2400 lines going out of plus q, hello, 2400, do you understand? By 6, how much is that? 400. 400 will be going to this, 400 will be going to this, 400, like that, flux is same. But if I move a little off center like this, all the 2400 lines will go through the surface, through the 6 faces, but they don't go equally through each face, because the moment I move it, the solid angle changes. Solid angle with each surface changes. Will it or not?
Yes, sir.
R change, try to understand. Hello. God only knows. We'll see. So much I'm talking simply, slowly, but I don't know. All right. Children, tell me. So that's all for today. If you've written down, I'll close the session.
Done.
P. Vaishnavi.
Yes, sir.
Vamshi.
Yes.
Now we are almost ready to apply Gauss law. I did what all is required. Only I did not prove the 2 pi into 1 minus cos theta yet. But if there is no response, I'll be talking to myself.
Thank you, sir.
Thank you, children.